So if you have the problem of holes, that whenever a process it leaves, it creates a hole behind it, and if many processes leave from different places in the RAM, then there can be different holes existing in the main memory at the same time. What will happen if a new process comes? In which hole would you put that process? So there are different techniques to choose one of the holes if there are many for putting a process inside it. Now these three techniques, there are three techniques, and they will choose one of the holes according to a criteria. The first one is the first fit, then you have best fit and the worst fit. The first fit, it will choose that hole because we assume that the operating system has a list of all the holes. So this list will be in some sorted order, for example from lower memory to upper memory. Okay, so the first hole will be down the memory, then going up a little bit in the memory there will be second hole, and so on. So the first fit will starts from the first hole, and it will see if the process can fit in there. If the process can fit in the first hole, it will assign. If the process is bigger, then it will go to the next hole, and any first hole in which it can find enough space to put this process in, it will use that to assign that to this process. The second strategy is about best fit. Best fit means you will search among all the holes and find the smallest hole which can fit this process. Why is this useful? Because in this way we can actually make sure that after fitting this process in the hole, we have the smallest possible leftover memory, or the new hole which is created after fitting in this process, it will be very small size. So the wastage of memory will be reduced, the chances of wastage will be reduced. The third thing to consider is to allocate the largest hole that you can find. So it is opposite of the best fit. Again, you have to search in the entire list, and the advantage of this apparently is that in best fit we will produce the smallest hole, in worst fit we will produce the largest leftover hole. Why do we do this? Because it may mean it may result in the fact that the largest hole which is left over can now accommodate a new process. In the best fit, maybe the smallest hole may be very small and it may not be able to accommodate any process, so the remaining hole will be actually useless. And here the idea is that the new hole is big enough to actually be allocated another process. But using experiments we see that first fit and best fit, they are better than worst fit, both in terms of speed and usage of main memory. Now we discussed about this problem in the last slide, that when, for example, in the last diagram which is on the right side, okay, you have one hole, and let's assume that the process 9 or process 5, it also quits the system. So in this example we have two holes. Now maybe these two holes are actually very small, and if a new process comes, the process may be not be able to enter into any of these holes. What we can do is that together these two holes, they can be combined to make bigger hole, and the new process can come inside. But two separate holes, they are smaller than the size of the process. So how can we do this, that if there are more than one holes, we can combine them together to make bigger enough hole so that any new process can come and be allocated this space. This is done using one process, but before telling you the process, we also have another type of this hole. So the one I explained to you, okay, this problem when you have small memory holes in different places in RAM, this problem is known as fragmentation. So fragmentation means there are small fragments of memory which are here and there, located here and there in the main memory, and there we have two types of fragmentation. One is known as the external fragmentation and the other one is known as the internal fragmentation. The example then that I just gave to you about a process quitting and leaving behind a hole, that is known as external fragmentation, in which case actually there is memory which exists there in the RAM, but it is not actually enough to satisfy any request, because the spaces which are there in the form of holes, they are not contiguous. We are considering contiguous memory allocation, and contiguous memory allocation means that you bring in the complete process and you put it at one place. Okay, so the process cannot be divided into different parts, only a single part of a process, and you put it somewhere in the RAM. So after creating many holes in the memory, you have different memory fragments, but each of the fragment is small, and a new process, it cannot be accommodated. If we can combine those fragments, okay, as I explained before, then it is possible that we get additional bigger space and new processes can be accommodated. So this solution to external fragmentation is known as compaction, and there is a diagram which shows this idea that on the top you have the fragmented memory before compaction. So you can see 4 different holes, okay, in the gray color. So this is one small hole, one small hole, one small hole, and finally another small hole. Now these are 4 different locations. Let's assume that we get a process something like this size or this size, okay, any 2 sizes. You can see a new process of this size. When it comes, there is not enough space in any of these holes, so we cannot accommodate this process. But what we can do is to compact the memory, which means that we move all these processes which are there adjacent to one another, and so the free memory spaces, they are then allocated one place only. So you can see that after compaction, the diagram below, it has only one free space, and those processes which were there, they have been allocated adjacent spaces. Now you can see we have a bigger space, and any of the process size which are shown in the example, the existing ones, if a new process comes of the same size, they will be placed in this area. That is the advantage of compaction. Now there is also another type of fragmentation which is known as internal fragmentation. What happens in internal fragmentation? It is actually related to the allocation of a process to free memory space. For example, let's assume that the operating system can give free memory space in terms of megabytes, 1 megabyte, 2 megabyte, 4 megabyte, etc. Okay, it cannot give the memory space in terms of kilobytes because of different reasons of programming, okay, or process management. So let's say the smallest memory area that can be given by the operating system to any process is 1 megabyte. Now if there is any process which wants memory space but the size is less than 1 megabyte, say 800 kilobyte, and you give 1 megabyte space to 800 kilobyte process, then the remaining 200 something kilobytes, they are wasted. So this is known as internal fragmentation, and internal fragmentation can result for different processes if you give actually fixed location or fixed size of memories to different processes. So this is internal to any partition, because an operating system can create a partition of fixed size and the processes can be smaller than the size. So this will result in the internal fragmentation. And if we use first fit analysis, then it says that if you have n blocks allocated to processes, then almost half of those n blocks are lost due to fragmentation. And there is a rule which is known as 50% rules, which says that 1/3 of those partitions may be, or memory may be, unusable. Okay, so this is just a rule. You can see more details about this rule and its discussion in the book. So we discussed about the fragmentation issue and a solution to fragmentation, which is known as compaction. These issues, they arise for this partition when you have contiguous memory allocation. Remember, this is one form of allocation of memory which is known as contiguous memory allocation. The next thing is about paging. What is paging? The problem with the contiguous memory allocation is that here you assume that the process consists of one block and you bring in the whole block into memory. Now this is inefficient because of the reason that the process may be very big, you don't find enough space, or it may take a large amount of time, okay, to bring in the process, etc. So an alternative design, which is very good design technique for allocating memory to processes, is the paging technique. What we can do in paging is we divide the logical memory of a process into pages. So instead of seeing the process as one block, we have one process consisted of many pages. And the good thing is that we can allocate memory to these pages into different parts of the memory. They need not be together or contiguous. So I will show you the example how we can distribute these pages into memory. But the good thing is that first it avoids external fragmentation because they don't need to be contiguous, and then also it avoids the problem of varying size memory chunks that I'm going to explain next. So what we do is that because we divide the memory of the process into pages, we also divide the physical memory into similar fixed size blocks, but they are known as frames. So the idea is that a process has a page and the physical memory has a frame, and what we do is we take a page, any page, and put it anywhere in the physical memory into a frame. So the size of the frame and the size of the page, they are exactly the same. So what do we use for page and frame sizes? Normally it is the power of 2, because computer works in the form of power of 2. So that is our favorite way of choosing the sizes in computer. So normally this is between 512 bytes and 1 gigabyte. Can you tell me, if we use the power of 2, just listen to this question, okay? If we use the power of 2 and I want to create addresses of 512 bytes, so how many bits do I need to create 512 bytes of data using the power of 2? 1 kilobyte is how much? 1024. Okay, 1024 bytes is 1 kilobyte. So 2 power 9 is 512. 2 power 10 or 1024, this is 1 kilobyte. 2 power 10. Can you tell me 1 megabyte? How many bits? So actually 1 megabyte is 1024 kilobytes. Okay, when you have 1024 kilobytes, that's equal to 1 megabyte, and you know that 1024 is 2 power 10. So if you take only 2 power 10, that's 1 kilobyte. If you take more 2 power 10, that will be 1 megabyte, which means 2 power 10 and 2 power 10, okay, this is 2 power 20. So 2 power 10 multiplied 2 power 10, that is 1 megabyte, 2 power 20. So can you tell me now what is 1 gigabyte? Yes? 30, exactly, yes, excellent. So 1 gigabyte is 2 power 30, which means that if you have 30 bits, with 30 bits you can have addresses in the range from 0 to 1 gigabyte. Okay? Similarly, 31 is 2 gigabyte and 32 bits is 4 gigabyte. Okay, so if you have 32-bit computer, it can have up to 4 gigabyte of memory, and more than 4 gigabyte it cannot support. Remember, so old computers which were 32 bits, they could not have more than 4 gigabyte of RAM. If you have old computer, just check it. you will not be able to get more than 4 GB of RAM on 32-bit computer. Now, for past many years, you have newer computers in 64-bit, and 64-bit, you can guess it is up to several terabytes of RAM. Okay, because 40-bit it is 1 terabyte, so 50-bit is I think petabyte, and 60-bit is exabyte, etc. But that's quite a big memory addresses. It can be accessed by 64-bit of address spaces. Now, as I explained, that we have the logical memory, we divide into blocks of same sizes, and each block is called a page. And similarly, the main memory, the physical memory, we divide into the same size of block, and each block is known as a frame. So our idea is that when we load a process into RAM, we load it in the form of pages. Okay, so depending upon the size of page and depending upon the size of the process, we can have many pages in one process. Okay, so if there is a big process, it can have many more pages than a small process. And the idea is that when you load a process, you don't load all the pages at the same time, but actually you load only the initial pages which are needed. So you will load, for example, 2 pages or maybe 10 pages, let's say, in the RAM. You don't load all the pages at the same time. When there is a need to run the code into a page which is not loaded, you will load that page into the RAM on demand. Now, it is important because you have different pages. Some pages may be in the RAM, some pages they may be in the hard disk or not yet loaded. Okay, so the operating system, it needs to keep track of, first it needs to keep track of all those pages which have been loaded and not loaded, and second, all the free frames in the physical memory, because whenever a new page is loaded, it must be loaded into some free frame. If free frame is not there, what we will do, that is we are going to study next in chapter 9. So to run a program which has n pages, we may need n free frames and then load the program. Now here we assume that we are loading all the pages at the same time in this chapter right now. Okay, what I told you that we will discuss later, that we will load only few pages, but here we assume that we will load only we will load all the pages, and for each page we will need a free frame. So we need a page table that will actually be a mapping between logical and physical addresses. Okay, so each page can have many addresses depending upon the size of the page. Here we can see, let's say the page size can be 512 bytes or it can be 1 gigabyte. So where is each address in a page? It can be found in the physical address. For that we need a page table. And just like main memory, the backing store or the virtual memory is also split into pages. Okay, and the problem is that in this scheme of paging, we can still suffer internal fragmentation. We can reduce the external fragmentation because we can assign any page size block to and that is a frame actually. We can assign any frame to any page anywhere in the RAM, so there is no issue of contiguous memory problem that we had before. There is no need for compaction. Now, how do we design this scheme? Actually, we have that in this case the address which is generated by the CPU. So, for example, it can be 32-bit address, it can be 16-bit address, whatever it is. We divide this address into 2 parts. One part is to denote the page number in which this address is. So this address can be in the page number 0 or the page number 1, etc. Okay, and the second thing is about the page offset, which means that within this page, where is the address? Okay, so a page may have 1000 addresses. So is this the address number 0, address number 1, address number 10, etc. So that is actually the offset into that page. Now the total what we see is here the page number has some number of bits, and we can say that if the address is, let's say, M, so if we denote only M to the page offset, so the remaining M minus N is used for the page number. M can be, for example, 10, and if you choose N to be 4, then the size of P can be 10 minus 4, which is 6. So which means that 6 bits can be used for page number and 4 bits for the page offset. Similarly, we can choose 6 bits for the offset, N is equal to 6, and M minus N, which is 4, we use it for page number. So what difference does it make? Can you think of it? Just think about that. If I increase the number of the page number size, what will happen? Okay, because when I increase the page number, then size of page number, then the page offset will be decreased. Okay, if I increase the page offset, then the page number will be decreased. It's the same number of bits, in this example 10 bits, and I divide these into page number and page offset. So it can be 3 for page number, 7 for page offset, for example. It can be 7 for page number, 3 for the offset, etc. So just think about this. What will change if I change the number of page number bits or the page offset bits? Now, in general, if you have any logical address space, then we have 2 power m is the logical address space, and the size of page is 2 power n. Okay, how does this happen? We are going to see this, inshallah, in the next few slides. So here is the example which explains this. The CPU, it generates logical address that we know before. Even in the beginning of this chapter, we said that the CPU generates a logical address which is converted to a physical address which is found in the physical memory. Now here, when the CPU generates a logical address, it is divided into 2 parts, the page number and the offset. Page number is D and offset is page number is denoted by P and offset is denoted by D. So in this simple example, you can see there is a page table, okay, and the index of the page table is P. So here on the left side, this is P, and inside the page table there is a reference of F. So if a P comes, P can be 0, 1, 2, 3, whatever number, we will go into that index. So index 0 will be here, index 1, and so on, okay, according to the size of the page table. So if the size of the page table is 100, we can have from 0 to 99 over here, and inside that value for P we will find F. Okay, so this F we will take instead of the P, because P and F have the same size. So this page will be located into some frame, and the D will remain the same. Okay, so the value of D inside a page will be the same as the value of D inside a frame, and this physical address we will go and find the frame number, and for this frame number we will find the offset inside the frame, and this will give us the corresponding physical memory address. Now this is just a scheme to show to you how does it work actually. Let's see another example. What do you see here is that your logical memory on the left side, okay, that's the memory of a process. It has 4 pages, page 0, page 1, page 2 and page 3, and then in the middle you have the page table. The page table shows which page is in which frame. So page 0 is in frame 1, page 1 in frame 4, page 2 in frame 3, and the last page, page 3, is in frame 7. And these frames 1, 4, 3 and 7, they are actually the frames in the physical memory. So you can see in the last portion, the right side, okay, this is the physical memory, and against each of the frame number, you can find the page number, and this mapping was done here. So for example, this page 3, okay, how can I find it in the RAM? I will start looking this page 3 by going into the page table, it will give me this 3, and this 3 gives me actually number 7. So I take this number 7 and I go to frame number 7, and there I find that the memory, the frame number 7, it contains the page 3. So if I change this 7 to 5, then the page will come here, for example, or it can be 0, it can be 2, anywhere, wherever is there any free frame, this page can be put inside there. So that's the basic idea behind paging, okay, and how do you map the model for mapping a logical page or a page in logical memory into a physical memory. So another example, this one, it shows the pages as well as the addresses or offsets in the page. So in the logical memory here, actually this one block, this represents a page, okay, so I will denote this by P, and inside this P you can see there are 1, 2, 3 and 4 offset addresses, okay. Each offset address has its own address. So this is the content of the address, A, B, C, D. This is what is inside the program, and 0, 1, 2, 3, this is the address or the offset address inside this page. So this is page 1, then you have similarly page 2, okay, and you have page 3, and finally page 0. This was page 0. Let us start with page 0, okay. Then this one should be page 1, okay, and this one I should delete it, okay. So let me delete this 3 and 4, and we will call it page. So this will be page 0, the second page will be page 1, this is page 2, and finally page 3. This is the same like the example before. So I have these 4 pages, and I have a page table again which has 4 pages, and this time you can see that page number 0, it is assigned the frame 5. So we choose frame 5, and how do we choose it? We will start, this is my page, frame 0, frame 1, frame 2, frame 3, okay, frame 4, frame 5, okay. So this is my frame 5. Let me finish it for frame 6 and frame 7 as well. So overall there are 8 frames, and I can see that page 0 is in frame 5. So here this is my page 0. So this is page 0. Similarly, page 1 is in frame 6, which is starting from the address 24, okay. Then you have page 2 in frame 1. This is my frame 1, and page 3 in frame 2. So I have these different pages on the left which are assigned different frames in the physical memory. So how do you find any logical address? Let's say you want to find this instruction number 6, which is G. Can anyone explain to me how can I find this G? Where is this in the RAM? Yes? Where is this instruction G in the RAM? Anyone? Instruction G, you can see this has address 6 in the page. What is the address of instruction G in the RAM? Can you tell me? Sorry? Okay, so you don't know. How do we find this address which is for this instruction G into RAM? Let me explain this. First we find that this instruction G, it is in page number 1, okay. So first we see that the page number is 1, and then we will go into the page table and see here that page 1 is actually frame 6. So from page 1 we will find that the frame number is 6, okay. So frame is 6. Now this 6th frame, where is this located in the RAM? So we will multiply this. Okay, we will multiply 6 by page size. What is the page size? Can you tell me? Okay, so page size is 4. Okay, here. So we will multiply 6 by 4. Okay, so when you multiply 6 by 4, this will give you the address of 24, which means that at location 24 you will find this page, which you can see here. So at location 24 you will find this page 6. Now inside page this is frame 6, sorry. Inside page 1, the offset of instruction 4 is 0. The offset for instruction 5, so 4 is 0, then you have 5, which is 1, and you have 6, which is 2. So it is offset 2 from the start of the page. So we will find here that D is equal to 2. This is the offset. So D is equal to 2. Now we will use the same D in this frame, which is on the address 24. D0 is E. Okay, this is D0. D1 is F, and D is equal to 2 is what we need. So we will find G over here in frame number 6 and offset 2. So this is how you do a mapping from an instruction in the page to a frame in the to an offset in the frame in physical RAM. Now I told you that in paging we don't have external fragmentation. External fragmentation was there when we had contiguous memory allocation. Contiguous memory allocation had the problem that you had the whole block of the process into RAM. Here we have divided the memory into small pages, so the page can be anywhere and we are not restricted to use specific holes of any size, but wherever the page can fit, which is usually a small area, so you can put it there, and so we avoid external fragmentation. But we discussed that we can have internal fragmentation in pages, and as before I explained to you that internal fragmentation means that if the operating system says that the size of the page is, here in this example, 2 kilobyte, 2048 means 2 kilobytes, so the size of the page is equal to 2 KB. So the question is that if I have a process whose size is smaller than 2 KB, let's say I got a process whose size is 1 kilobyte. Okay, so this process needs only one page, okay, because its size is very small. The size of page is 2 kilobyte, the size of the process is 1 kilobyte. So if you put that into a page, it will take one page only. But the problem is the size of page is bigger than the size of the process, so 1 kilobyte is used in the page, the remaining 1 kilobyte is not used, and that becomes the useless space, and you cannot give this space to another process because in one page you can only have one process, so it means that 1 kilobyte is wasted. Similarly, if you think about a process whose size is 4 kilobyte, so 4 kilobyte means you need two pages. In one page 2 kilobyte and another page 2 kilobyte. If you have 8 kilobyte process, then you can have 4 pages, 2 kilobyte, 2 kilobyte, 2 kilobyte, and last one again 2 kilobyte. 4 pages of 2 kilobyte each, that will become one process of 8 kilobyte. So this is good multiple if you have in page sizes as multiple of 2, 4, 6, 8, 10, etc. But if it is more or less than the multiple of 2, for example, instead of 10, if you can have 9 or if you can have 11, or in between them a little bit more than 10 kilobyte, maybe 10 kilobyte and a few instructions, okay, then there will be actually the internal fragmentation. So for 11 kilobyte you will use 5 frames for the initial 10 kilobyte and 1 frame for the 1 kilobyte, and the 1 frame for 1 kilobyte, because the size of the frame is 2 kilobyte, 1 kilobyte will be used and 1 kilobyte will remain useless. and here is the example of process size which has 72,776 bytes. So if the size of the page is 2 kilobyte, so you will need 35 pages. Okay, so 35 pages is about 71,000 something, 71,680. Okay, that will be the size taken by 35 pages. So 71,680 will be allocated in 35 pages, and then there will be 1,086 bytes remaining. This 1,086 bytes, this is less than 2048 bytes, but because you have to give it any page, so you will just give it one more page. So this process will then take 36 pages. Okay, and the remaining size, which means that the page size is 2048 and you use only 1086, so this 962 bytes, that will be the result of the internal fragmentation. Now in worst case, let's say your size of the page is what we see here, 2048 bytes, but you have a process whose size is 2049 bytes, just 1 byte more than the page size. What will happen in that case? That is actually an issue, because you cannot put 2049 bytes into one page. So what will happen is that the 2048 bytes of the process you will put in one page, and the last byte, which is one more than 2048, you will put into another page. So the new page, the second page, it will be using only 1 byte. 2047 byte will be useless. They will not be used at all. So that 2048 byte of memory, that you cannot use. Okay, so which means that in the worst case you can have one frame for only 1 byte, and that 1 byte will take the complete frame, and this is the worst case fragmentation. But on the average, some pages, some processes, they will take almost complete frames. Some they will take frames in which 1 byte is used, for example. So on the average, we can consider this as half frame size. Okay, which means that in this case it will be only 1 kilobyte of memory used for each process, which will be wasted in the internal fragmentation. So if your process size is bigger, let's say you have 2 megabyte page size, then the worst case size, the average fragmentation will be 1 megabyte. If the page size is 2 kilobyte, it will be 1 kilobyte. Now the difference between 1 kilobyte and 1 megabyte is very large, which means that using small page sizes you will waste less amount of memory, and using big page sizes you will lose large amount of memory. So should we choose small size? Okay, because small size means that less loss of memory. The problem is, if the frame size is very small, then the page table, it may take a lot of memory because there will be many pages. So the entry table will become very big. There will be many slots for each page, for the overall pages, and that is also not manageable. Also, because we see that as the years are going on and there are new processes created, like games, bigger games and movies, etc. So the page sizes, they are growing over time. Like maybe in Windows 98, maybe the process size was only a few megabytes. Then the Windows 2000, there were many megabytes, and now in Windows 10 normally we use processes which are several gigabytes. So it means that the page size is also growing with the time. If we consider the Solaris operating system, then it has 2 page sizes, 8 kilobyte and 4 kilobyte. Why? Because for small processes we will choose 8 kilobyte, there will be less wastage of memory. And if we have bigger processes, which takes a lot of size and pages, so we will choose the larger page size. In this way it will be easy to manage the number of pages. So for 8 kilobyte page size, there will be small number of processes and small number of pages, or a little more than small number of pages, but at least there will be less wastage of memory. And if you have very big processes, then again using 4 megabyte, it will not result in too many pages, and the management of pages will be easy. Now we have a different view of process and physical memory. So in a process, the pages will be arranged in one order, and the physical memory, they can be totally different. So we have to have some implementation so that the process can access its own memory, because memory protection has been very important. We have discussed this many times. This scenario explains the concept of free frames and how they use it. If you look closely, we have two diagrams here, A and B. In diagram A, we see the things before allocation, and diagram B, it is after allocation. Okay, allocation of what? Allocation of frames to a new process. So if you consider the left side, we have a new process. It has 4 pages, and there are some free frames in the RAM. These gray color, they are free frames. The blue color are the frames which are already used by other processes or the operating system. So how many free frames I have? I have 1, 2, 3, 4 and 5, and the frame number is given on the left side. So the operating system has actually a free frame list which says that here, for example, frame 14, 13, 18, 20 and 15, they are free. So I have 5 free frames, and a new process with 4 pages comes. So you can see 5 empty frames, and I need only 4 frames. So we can assign the memory to this new process which has 4 pages. So that was before allocation. After allocation, you can see that these pages, page 0, from page 0 to page 3, they have been allocated randomly. Now how do we allocate this? This is random, done by the operating system. And we have this page table for the new process which has a mapping of this page number to frame number. So page 0 is in frame 14, page 1 is in frame 13, page 2 is in frame 18, etc. And before, the operating system had a free frame list. Now the free frame list has only one free frame, which we can see is the frame number 15. So if any new process comes and it needs only one page, we can assign that process to this location. Otherwise, if it is more than one page, then we cannot assign that process, and we have to do something to make some free space or whatever solution, but that we will discuss in the next chapter. Coming toward the final topic, these last 2 slides of this chapter, the concept of shared pages, okay, and what is the importance or need of shared pages. So here you can see we have an example. If I tell you the example of Microsoft Word, okay, it is possible for you to open several Microsoft Word documents at the same time. So maybe you have 2 assignments, homeworks, or maybe you have a homework and some other document in which you are working. So you open them together at the same time, which means that you will see 2 Word applications. So actually Word itself is only one application, but because you have 2 documents, so each instance of the Word application, it will have one document. So at the same time, you are dealing with more than one document. Now the document itself, it has different data. In one, you are doing homework of one subject, and in another document, maybe you are doing the homework of another subject, and in the other documents, you are doing something different, okay? So the document's data is different, but Microsoft Word is the same in all of them. In all of these instances of Microsoft Word, what you can see is that there are the same toolbars, there are the same buttons, there are the same menus, okay? The page size, etc., they can be managed in the same way. Even though you can have small changes in them, for example, I can change the page size for each document differently, but most of the things, they are the same. So what if I use only one copy of Microsoft Word document in RAM, and for each of the data I have a different copy because data is different? So such type of condition in which you have a program which is read-only, this is known as a re-entrant code or read-only code, which does not change. So let's assume that the Microsoft Word code does not change, only the data inside the Microsoft Word execution process, it changes. So this code can be shared among processes. So one example is text editors like Microsoft Word or the compilers, because the compilers don't change. The compilers only use the data file of the source code and they generate the executable files or linked files. And other windowing system, for example, different types of when you create windows between different applications, they can share common things. So this is the same idea as we have multiple threads which have the same process space we discussed in chapter 4, I think. Also, it's useful for inter-process communication, because if we can have some pages which can share some application data that can share the pages between them. In this case, the process has two parts, the private code and the data, okay, which has a separate copy of the code and data which is private. Otherwise, the code which is not private, that is the shared code, that can be actually shared between the different processes. I will explain this with the example that I have three processes here, process P1, process P2 and process P3. For each one you have a page table, and the page table on the left side we don't write here, but actually this is page 0, then page 1, page 2 and page 3. For example, here you can see that page 3 of process P1 is in frame 1, so you go to frame 1 and you will see the page 3 which is data 1. This is page 3, data 1. Similarly, this one is the page 1, okay, so page 1 for process P2 is in frame 4, okay, so this is ED2, frame 4, you go to frame 4 and you will find ED2. For this process, let's say I have this frame 0 which is ED1, so page 0 is in ED1, so page 0 I check, this is frame 3, I go to frame 3 and I find ED1. But if you think about it, you will see that there is only one ED1, ED2 and ED3. For each of the process I have ED1, ED2 and ED3, which means editor pages. So let's say this is text editor like Microsoft Word. So 3 pages of Microsoft Word in this process, 3 pages of Word in this process and 3 pages in this process. They are the same. We assume here that Microsoft Word needs 3 pages, and 1 page addition of each process is about the data, which is the private code. Okay, so these 3, they can be shared by all those processes, which means that if you look, then the editor 1, editor 2 and editor 3, they all have 3, 4 and 6 in all of these page tables. So for these 3 processes, they refer to the same frames, which means they are using the same code of the editor for the 3 processes. Why is it useful? Because you don't have to load this editor again and again for every process. Okay, it is easy to load once and use for different programs or data, and also it will result in actually smaller usage of memory, which means that you can load many programs at the same time. So with this we finished chapter 8. This was about how we manage main memory, and now we will go into the chapter 9, which is about virtual memory. Any questions? Okay, so we will stop here. and we will take a break of